Today we're talking about how to interpret pH curves so we can quantitatively assess equilibrium. And our success criteria is being able to determine if a pH curve involves reactions of strong or weak acids and bases. So what a pH curve is it's a graph tracking the change in pH over time during an acid-base titration. There are a couple of key regions in any given pH curve. There is going to be a more or less vertical region, although this can be at an angle depending on what the exact chemicals involved in the reaction. And, at least in a monoprotic reaction, there will be two buffering regions as well. And those are the flat regions where the pH is not changing as dramatically even as you add more acid or base. Now, in a pH curve, the end point is the point in the titration where you have, as the chemist, stopped the titration from taking place. The end point can technically happen anywhere in the pH curve. If you are trying to do a chemical reaction to determine the concentration of an unknown substance through titration, you want the endpoint to overlap with the equivalence point, the point where you have neutralized all of the acid and base. The equivalence point on the pH curve is going to be the area with the greatest slope, so the region that is most vertically up and down. Now, if you're actually making a pH curve, the endpoint's not going to happen until you have completely neutralized and, in fact, swung far over from neutralization so that you are now on the opposite side of the pH scale. Pretty much every level of the pH curve also has these buffering regions. And what's happening in the buffer zones is that you're actually creating a chemical buffer, a combination of a conjugate acid-base pair that does not involve a strong acid or base and is able to resist pH change. Now, you will sometimes notice right at the very beginning there will be a slight curve. You don't see it on this graph, but you do sometimes see it on diploma graphs. It's really important that you don't mistake that beginning curve when the buffer is first being formed for reaction. And we'll get to why that's important when we start talking about monoprotic versus polyprotic acid-base curves. We often also include indicators in acid-base equilibriums. And the reason that we add these indicators to titrations is so that we can detect where the equivalence point of a reaction is. And acid-base indicators work great for this purpose because acid-base indicators are all weak acids of some form. They change color when they switch between their acid and base form, but really they're just any other they're a weak acid like any other. What makes them different is that most of them are complex organic compounds and they change color. And that color change as the pH changes allows us to detect when we have gone through a dramatic change in pH. We use these pH curves because they actually provide a lot of useful information. They tell us what the initial pH of a solution is. They can tell us the point at which an excess titrant is being added as soon as you've crossed over that equivalence point. They can actually tell us how many quantitative reactions are taking place. They can tell us how many equilibrium reactions are taking place too. And they can help us with selecting an indicator if we are testing out another acid. Now, the pH curve that we see in this first slide is a pH curve representing a strong acid reacting with a strong base. In fact, we have NaOH, our strong base, and we have HCl, our strong acid, being added to it. Not every graph looks exactly like this, though. We can also have weak acids and weak bases involved in these reactions. And What that really means then is that the exact location of the equivalence point will change. And you can see this represented on the graph. You can actually create 4 different graphs out of the green and blue segments on this particular diagram. The blue segments represent the presence of a strong acid or a strong base. The green segments represent the presence of a weak acid or a weak base. And you can see on the weak acid side, that's that curve I was talking about earlier. This is just the weak acid buffering out as you add the first bit of base into it. It's not an actual reaction taking place, and that does matter. So in the curve of a strong acid combined with a strong base, we're going to go from the blue segment to the other blue segment here. You'll see that the equivalence point is going to be 7 because a strong acid and a strong base neutralize to create water. But if we end up with a weak acid and a weak base, we're actually going to start higher up, closer to 7, even if it's at the same pH. And when they reach their equivalence point, it's actually going to change over from green to blue right here. And the equivalence point is not at 7. The equivalence point is actually going to be above 7 because we have a stronger base than we have an acid, so that the point where all of that acid gets neutralized and switched over to its other form, that's going to be at a more basic pH, because the weak acid doesn't contribute as much to the pH as a strong acid would. Same thing if you start with a strong acid, we start low on the blue, but then we're going to switch over to the green, and we can see the equivalence point here with the strong acid and the weak base would be below 7, which is the same thing summarized on this slide. If a strong acid and base react with each other, equivalence point hits 7 quite nicely. If it's a strong acid and a weak base, the equivalence point will be below 7, and if it's a strong acid or a strong base and a weak acid, the equivalence point will be above 7.